Hello, welcome again. We are solving GATE 2017 Aerospace Engineering paper. Question number 48 is air at 450 Kelvin stagnation temperature and at a rate of 50 kilogram per second enters the combustor of a turbofan engine and is burned with 1 kilogram per second of aviation kerosene, heating value 44 megajoules per kilogram. The specific heat at constant pressure for the incoming air and the burned products are 1.005 kilojoule per kilogram per degree Kelvin and 1.147 kilojoule per kilogram per degree Kelvin respectively. Considering 100% burner efficiency, the stagnation temperature at the exit of the combustor is equal to dash Kelvin in 1 decimal place. So by energy balance, heat released by fuel should be equal to heat attained by gases. So heat released by fuel is 44 into mf. Okay, mf is 1 kilogram per second. Okay, and 44 into 1000. And heat attained by gases is mf plus ma is equal to because finally there are gases and that is a mixture of fuel and air. So we'll take mf and ma, and this is the final heat attained by the mixture, and cpg is your specific heat of gases and T is your exit temperature, and ma minus ma cpa Ti. So ma is 50 and cpa is your now we'll take air here and inlet temperature of air. So T is your exit saturation temperature, that is 1138.73 Kelvin. So that comes out from this calculation we get 11338.73 Kelvin. Okay, next question 49. A single stage chemical rocket having an initial mass of 10,000 kg and specific impulse of 450 seconds is launched from the surface of the earth and has to reach the escape velocity 11 km per second at burnout. Consider G is equal to 9.8 meter per second square. If the atmospheric drag and the effect of gravity are to be neglected, the mass of propellant to be carried out by the rocket is equal to dash kg in 1 decimal place. From rocket equation we have Vb is equal to burnout velocity G naught ISP ln mi by Fn. So Vb is 11 km, so 11,000 meter, and this is 9.81. This is your 450, ISP is 450, and ln mi by mf. Okay, so mi by mf comes out as 12.08. So mi is your 10,000 and mf is your 12.08, and mf is final mass is 827.618, and this is initial mass. So mass of propellant is final initial mass minus final mass, that is 9172.38 kg. Okay. Next, a centrifugal compressor requires 1800 kilowatt of power to compress 10 kilogram per second of air. Consider the world velocity component is equal to the impeller speed, that is no slip and no losses in the impeller. If the impeller has to rotate at 1900 radian per second, the diameter of the impeller is to be dash meter. So when there is no pre-whirl and no slip, power is given by mass per into u square, and power is 1800 into 1000, and mass per 10, and u is your u comes out as 424.26 meter per second. Okay, so this is the velocity of blade, and velocity of blade is given by omega into r and omega into d by 2. So d is your 0.4465 meter. So answer is 0.4465 meter. Next, an aircraft wing is idealized as a cantilever beam of constant width and length L with a tip mass of weight W Newton, and has uniform distributed loading of Q0 Newton per meter as shown in figure. The flexure rigidity EI and Q naught L is equal to 10 W. The upward deflection of the tip of the aircraft wing under given loading can be expressed as delta is equal to K WL cube by 3 EI by EI. Sorry. The value of K is in 3 decimal places. So this is your UDL of Q naught, and this is your we can say it is UDL and this is W. Taking uh, taking a point at a distance x, so moment at this point is Wx minus Qx Q naught x square by 2. So strain energy will be mx square dx to EI as it is varying from 0 to L. So put in the limits, so Wx minus Q naught x square by 2 square divided by 2 EI dx, and deflection at tip is curly by curly W 0 to L and 2 Wx minus Q naught x square by 2 x by 2 EI. Okay, and the limits are sorry we can take this out because it is a constant, and this is Wx square minus Qx cube by 2, or W putting the value, so integrating it, it will be WL cube by 3 by 3, and this will be Q naught L 4 by 8. Now Q naught is given as Q naught L is given as 10 W, so we can put here Q naught L as 10 W. Okay, after taking LCM, that is 30 WL cube and here WL cube. So minus 1 by 12 minus 11 by 12 WL cube by EI. So deflection. So now comparing from the given equation, that is K WL cube by EI, and delta is your so K is your 0.916. Answer is 0.916. Next, for the state of plane stress shown in the figure, the minimum principal stress is minus 7 meganewton per meter square. The normal stress sigma x in meganewton per meter square is equal to dash round of 28. So this is your 21. Okay, and this is 56 sigma n. Okay, and minimum principal stress is sigma 2 is sigma x plus sigma y by 2 minus 1 by 2 sigma x minus sigma y square plus 4 x y square. So that is given as minus 7, and sigma x is not known, and sigma y is your 21 MPa, and tau xy is your 56 MPa. So putting the values here, the only unknown thing is your sigma x. We use that formula straightforward. Okay. So sigma x comes out as 105 MPa.